Hi everyone, so today I'm going to be talking to you about different ways that manufacturers are using 3D printing in their workflows, and we're going to talk about it in the context of desktop printing and how that helps manufacturers reduce costs, save time and money, and all the way from concept to production. So traditionally, it's difficult to achieve clear communication on new parts or products. There's a lot of effort that goes into managing external vendors and supply chains, and those supply chains can be complex. They can have unpredictable lead times. So additive helps to clear up some of these problems or improve your manufacturing processes. After today, you should come away with some ideas of how to improve those communications and collaborations, even if your team is spread out globally, how to save time and money by bringing jig and fixture production back in-house, sort of looking at vertical integration, and have a roadmap of how to unlock organizational efficiencies that create more value for you and ultimately more value for your customers. So the agenda today, we'll be talking about these 5 categories of how additive technology is used in manufacturing: prototyping, communications, and manufacturing validation, jigs and fixtures, then digital inventory, spare parts and reverse engineering, end-use parts, and organizational innovation. So a bit of background on me. I'm Andrew Edmond. I'm an applications engineer at Formlabs. Prior to that, I ran a product design and development company called Clear Design Lab, where we'd help companies go from concept all the way through to manufacturing. What is Formlabs? Formlabs, we've been around since 2011, and we're really focused on making reliable professional tools in the additive space for a variety of professionals. So today I'll be speaking mostly to manufacturing applications, but these machines get used across all kinds of industries, all kinds of different companies, from consumer products to medical devices and industrial companies as well. So an interesting thing with 3D printing is just how much the cost of the technology has fallen and how much more capable the materials are. So as those changes happen, as the machines become more cost effective, new applications open up. So this is kind of a cost curve that we look at in terms of applications that make sense over time. And right now we're kind of in this general dental area where it makes sense there, and limited run consumer production. Near future, looking at things like mass customization, and eventually getting parity with universal production where it becomes cost effective as an end product manufacturing technology. But for right now, you can see we're already in the space where prototyping definitely makes a lot of sense, production jigs makes a lot of sense, and certain aspects like patient-specific things like surgical implants or audiology are also cost effective with 3D printing. So Formlabs, we make right now our Form 2 desktop SLA machine and wash and cure for cleaning off those parts after they're done printing and bringing them to full mechanical properties. We also make print preparation software called Preform, which you can see here, and I'll talk about a bit in this presentation. And what SLA is really good for is getting really fine surface quality, so really good smooth surfaces, fine features, better than almost any 3D printing technology in that regard. So you can see here a printed part. So it's been used for a long time for prototyping and product development workflows. This is an example of a prototype fan, all printed with SLA resins. And the materials are advancing a lot too. So just as the cost has changed and the cost of the technology has come down, there have been significant advancements in the material properties and what you can do with SLA printing resins. So this is, as an example, is our ceramic resin. It's a filled resin that actually has ceramic in it, and then you print the part. It's in a green state. You fire it to burn out the plastic component, and you're left with a net part that's all ceramic. So first application we're going to talk about today is prototyping, communication models, and manufacturing validation. So as I mentioned, prototyping has been an application for a long time for 3D printing, particularly for SLA, because you can get those really thin walls and fine features and things that you're familiar with for plastic part design. But also it gets used for communicating. So whether it's internally with your own manufacturing team or externally with your customers to communicate on things that might need to change from a DFM perspective. The old way is to use dimension drawings, which requires a fair amount of worker skill and experience for accurate interpretation. And that's really even more so when you have complex parts. So if you have a complex part with a lot of callouts and a lot of fine features, getting that full perspective can be a bit cumbersome to page through. And those small features just are hard to be legible in some cases. So more and more we see companies using a combination of drawings and physical models. So they print out a model that can be handled and passed around, and you can talk through the features to easily illustrate the steps in a manufacturing process or an assembly process in a less cumbersome way. So they're also easy to share, whether that's internally or externally. We see this being done with remote teams or field offices that are scattered around the country or around the world. And these can also be used for manufacturing validation in terms of surrogate parts or setting up a line for manufacturing where you're waiting on components from a vendor. You can put those sample parts in place and get a sense of how that line will run before your consigned parts come in. So this is a quote from one of our customers at A&M Tool. They make parts for NASA, for Boston Dynamics, for a bunch more companies, and they have a lot of machinists, and they've come to rely on printed models to help communicate those callouts and features. So this is another example from A&M Tool. This is in their fabrication division, so this is one of their welders with a scaled down version of the assembly that they're ultimately producing, and this is just a really helpful tool for them to quickly communicate at a glance how something should come together, how it should look, even at a reduced scale. It can save a lot of time and headache. The other bit of this is kind of manufacturing validation, so producing your real part geometries and real materials with minimal tooling. So you can also print molds for injection molding or other types of manufacturing processes to quickly get a couple of parts made, shoot real plastic into that mold that was off of a Formlabs printer and validate that the part geometry works as expected, that the mold flows as expected, and get your DFM questions answered. In the case of something like overmolding of a PCB, you can print the surrogate part for that, so it's just a placeholder, mold around it, and evaluate how that manufacturing process is working without sacrificing a really high cost or high value component. This is an example of a simple USB enclosure with a printed mold in our high temp material. So this is again an example of just how the material properties have changed in these technologies, and you can now print things like tooling for at least a manufacturing validation to get a couple of parts to check out. Spare parts, digital inventory, and reverse engineering is something we see more and more of for manufacturers. So downtime is a really big issue for any manufacturing organization. You don't want to have machinery sitting idle, especially at the wrong time. It can be very costly. So increasingly we see companies that are digitizing the models and part geometries that they rely on so they can print them and maximize their uptime. If you have a legacy product, an old product that's maybe not supported, which is quite common in manufacturing environments, you're using tools across decades or longer time span, and those aren't always well supported or maintained by the original equipment manufacturer, so being able to support those internally can be really beneficial. And in some cases, we even see people taking that part geometry of that maybe old equipment, that certain part that fails a lot, they'll actually change that geometry to improve the performance so that it doesn't break in the same way, and you can have better uptime. So this ties into digitizing inventory, where you can build identification numbers right into the part, and with that version info on the part, any worker in your facility can easily go to a printer and get a new part made by pulling the same file with the same orientation, same support structures, so that you get repeatable results. It also makes it easier for managing inventory. If you have jigs and fixtures, you don't have to keep them all in storage. These are really low cost parts, so they can just be reprinted as needed. So this is Dashboard. This is an example of our software that helps you to organize a bunch of printers across an organization, whether it's in one location or spread over multiple locations. You can see different resins that you're using. You can pull up part information, as I said, stored with support structure and orientation. You can put notes in there if there was, an element of the part that was changed or an orientation that might work better. You can put those notes in there, so it's easy to work collaboratively across different locations. This is a photo of our printers on site at Pankel Manufacturing. So they make a lot of jigs and fixtures for their line. They're an auto parts and aerospace parts company. So they make parts for a lot of different customers, and they've switched a lot of their jigs to printed parts rather than machined. And this is an example here. You can see part identification numbers both on the engraved bases but also on the printed parts themselves, so they're easy to identify if one wears out or needs to be replaced. So reverse engineering is, again, a way of digitizing your inventory or digitizing parts that you might already have, whether that's to make things fit components better or designing a new part that works in an aftermarket setting. From there, jigs and fixtures, probably one of the most popular applications that we see. So as I mentioned, Pankel Manufacturing earlier, this is one of their jigs that for aligning turned parts that goes on an automated line. So these are parts that can really withstand a lot of mechanical stress and strain. This is an example again of just how much the material properties have changed, and they're much more resilient and impact resistant, so they can actually endure the stresses and strains of a manufacturing environment, whereas even 10 years ago, SLA resins weren't quite in that spot where they could be used in those kinds of situations. So where this really saves time and money is moving your workflow from a traditional workflow to an additive workflow. So when we're talking about a traditional workflow for making jigs and fixtures, you go from identifying a need to designing that jig or fixture, taking that part through a DFM process, sending out for quotes, getting your units ordered. Then your external vendor generally is going to produce those parts, ship them to you, and then they get deployed on your line. The issue with that is just there's often little changes or improvements that you could make once the piece is deployed, things that you learn from how your manufacturing team works, or maybe the part has changed a bit. And so if you want to make those changes, you have to go back through this whole loop again. Whereas an additive workflow that we see more companies moving to, they're bringing jig and fixture production back in-house because they don't need a skilled operator to run this printer. They can run it overnight easily on its own. And so they are more and more printing plastic parts to fulfill these jig and fixture needs. So in an additive workflow, you can go from identifying the need to designing the part. Generally, you don't have a DFM process that part needs to go through because 3D printing is really good at handling geometric complexity. You can have pass-throughs, you can have undercuts. Then you produce those units in-house and deploy them. So it's a much shorter process, a much shorter feedback loop. If there are changes that you want to make, they can be implemented the same day or next day. And there are cost benefits to this as well. So using Pankel as the case study here, they had 90% cost savings compared to outsourcing of machined parts. They reduced their lead times from 5 business days to 1 working day or less, which lets your lines get up and running faster or stay up and running. They also liked that they didn't have minimum order quantities to deal with, so they can replace parts one at a time rather than ordering them in lots and save on setup fees from their vendors that way. So to put it in context of a specific part, this is a simple nest part. In machined aluminum outsourced, you're looking at over $300 in HDPE, over $200 in tough resin. It's $12.60 in material. So this is the main material that Pankel was using for their jigs, and just saves you a lot of cost and gives you the convenience of doing it in-house. So part complexity can be dealt with at the part level. You can have things like hinges and pass-throughs, complex surfaces. Those are all easily handled by SLA and SLS printing presses, and really would be frequently very costly features to have if you're machining that part. And use parts, this is kind of looking more towards the future and where 3D printing is going and how it might impact manufacturing. It's still emerging, like I said in the beginning, with that cost curve. It doesn't make sense for a lot of applications yet, but more and more opportunities are opening up. So as an example, audiology, or whether that's hearing aids or earbuds, you want that to fit your ear specifically. That's kind of a patient-specific geometry or a consumer-specific geometry that you get much better performance out of it. You don't have earbuds that are too snug and uncomfortable, or too loose and fall out. So this is an example of using a Form 2 to print these really thin-walled shells that are a mold. So you inject silicone into this mold and it breaks away, and then you have an earbud left behind. So this is an example of just how customized it can get to fit specifically an individual's ear. So generally it's going to be these kind of customization applications where the current costs of 3D printed parts become better aligned with consumer pricing. because you're getting extra value and utility out of that customization and the resulting increase in the price point of the part. So we have a collaboration right now with New Balance where they're working on printing custom midsoles and plates to better fit athletes' feet so they can have better performance using direct printed midsoles and plates rather than molded parts, which can only exist in a handful of sizes. And to kind of facilitate some of this, we've been working on Formcell, which is a system for automating the removal of printed parts from a machine, and you can run multiple materials at the same time. They get washed and put onto a trolley, so it's really all about making the labor as minimal as possible. So when you're dealing with the complexity of all these orders coming in for something like earbuds or shoe components that are customized to an individual that are essentially batches of one, you don't have those being tracked through the system by a person. It's a very digital workflow, kind of a digital thread from where it gets ordered to produced and ultimately shipped out to that customer. So this is kind of a look at the equivalent of dashboard for Preform, which I showed earlier, our print preparation software. This is kind of the scaled up version for more of a manufacturing environment using the Formcell. So it gives you a rundown of all the machines that are running, where they are in terms of print job completion, if there are any errors that need to be checked on, what the resin levels are like. So it's a good overview for the minimal machine maintenance that needs to happen. The other end-use part thing to consider is SLS printing. So SLS printing is selective laser sintering. So you have a bed of powder, and that bed is heated up, and you have a laser that comes along and fuses those particles together to create your net-shaped part. And the great thing about that is it's a self-supporting structure. So you have printed parts that are self-supporting, gives you more geometric freedom. And in this case, you're printing with polyamide or polyamide 12 or nylon, so it's a really tough, resilient thermoplastic, which makes it useful for a lot of different applications that undergo a lot of stress and strain. This is an example of just how many parts you can pack in, so that's another advantage of a self-supporting printer structure, is that you don't have the room that's being taken up by support structures. You can nest parts much more closely and get a better throughput per machine. So the last point I want to touch on is just organizational innovation of how having these printers changes how you work and how your manufacturing team works. So just as in the case of traditional computing, moving from monolithic computational centers to desktop machines, kind of monolithic to distributed model, the same thing has happened with 3D printers. So when you don't have a big expensive machine that requires a technician to run it, when you have something that's really low cost and easy to use, it can be distributed across an organization in an entirely different way. And so in the past, you might have had kind of a gatekeeper that tended those printers. That would usually be like a product development team that was using those printers primarily because they're going through a lot of design and engineering iteration cycles. But now we see these printers in tool rooms, in R&D facilities, and on the production floor. And really what that does is it allows you to have a tighter feedback loop between tooling and production workers. So that kind of additive workflow that I mentioned earlier, it's really enabled by having these printers across an organization so that you can deploy those design changes really quickly and create a culture of continuous feedback and continuous innovation. And now with those applications outlined, you can begin implementing the additive solutions or expand on things that you might already be doing if you have 3D printers in-house, and figure out opportunities for your organization that make your manufacturing processes more efficient or nimble, and ultimately increase your profitability and be more responsive to your customer needs. So what to do next? Request a sample part printed in any of our resins. I'd recommend taking a look especially at the engineering resins, which are formulated to have higher mechanical properties to deal with stress and strain that you might encounter in a manufacturing context. And they'll send a printed part to you to evaluate, look at the surface quality, look at the mechanical properties up close.